speaker for the afternoon is Steve Weinstein from just down the road in Waterloo at the Further Institute, and he's going to be talking about decoherence and the non-emergence of classic.
Yeah. See, this talk makes both claims, so one of them is bound to be right. I want to just first thank the organizers, especially Chris and Ronnie, for having me and this nice group of people. I'm really looking forward to giving this talk here. A couple of people heard this a couple of weeks ago, Wayne and Gordon. But I've changed it a little bit, and my thoughts are still evolving, so I'm looking forward to your feedback. One comment, if you do have questions of clarification during the talk, feel free to interrupt. And if it's something I reserve the right to postpone and answer till later, especially if it's something to which I don't know the answer, in which case I'll postpone it till after the discussion section, probably till after I leave. Anyway, that's the ground rules. Let me get on with this. This is decoherence and the non-emergence of classicality. So, here's a little bit about the context. I'm trying to motivate this a little differently than I have in the past. The emergence of classicality is of, so I'll mostly just read this, particular interest to those who think that the world as a whole should be or is properly described by a quantum state. The environmentally induced decoherence program, this is as opposed to the decoherent histories program, purports to show how classicality emerges for suitably macroscopic quantum systems, and hence to explain how and why we observe classical behavior in spite of the fact that quantum mechanics permits apparently non-classical superpositions of either large objects and its entanglement of these objects with other systems. So in this talk I want to show, it's a sequence of things here, that generic subsystems already have the properties which the decoherence program calls quasi-classical. Sometimes the people working in this area just call it classical, because it sounds better. I'll argue that true classicality, which I will define, is explained by decoherence only in the sense that decoherence explains the persistence of classical states, or states, of quantum states which have classical properties. As for classicality, I'm going to argue that the phenomenon of decoherence to a preferred basis, so this is really the kind of, this is called einselection by people who work in decoherence theory, is a necessary but far from sufficient condition for quasi-classicality when you utilizes a stronger and more plausible sense of quasi-classical, one which doesn't make everything look, virtually everything look quasi-classical. And this is a sense associated with the strand of research in decoherence, which goes by the name of quantum Darwinism and environment as witness. There's all kinds of catchy terms associated with the concepts here because the main protagonist studied with John Wheeler. So, decoherence in general refers to the loss of coherence in the quantum state of a system as a result of interaction with other systems in general. Decoherence as a research program studies the various ways in which this can occur. Okay, so it's studying the results of certain kinds of interactions of various quantum systems with other quantum systems. In particular, typically, when one is going to look at the interaction of a subsystem with some other quantum system plausibly regarded as its environment, things around it. So Zed, Zurich, Jos, I can't pronounce his name, and Schlosshauer and others have claimed that the kind of decoherence associated with some arguably generic sorts of environmental interactions explains how and why certain systems, typically macroscopic ones, exhibit classical behavior. So in the case of Z, this goes back to, I think, 1970. And Zed has gone on to advocate kind of a form of many worlds interpretation. Zurich picked this up in the late 70s, early 80s, and has really sort of been carrying the banner for the program since then. And his interpretive commitments are more veiled, but they look obscure. But they look, if you push hard, they wind up looking nowadays like a form of many worlds interpretation. But that's neither here nor there right now. This is just a little bit of scene setting. Jost is sometime collaborator in Zurich. Schlosshauer is a younger guy who recently wrote a book called, I believe, what's it called? Decoherence in the Quantum Classical Transition? Something like that. In any case, nice book. So what does it mean to say that decoherence explains classical behavior? It can mean one of two things, and I think this is a useful distinction to make. Either decoherence explains why macroscopic objects are effectively classical, or decoherence explains why macroscopic objects look effectively classical. So this is supposed to be, this would be a more ontological claim about classicality. This is a more epistemic claim, one which is more concerned with saving the phenomena, as it were, saving the appearances. Why do we see things that look classical? Why are they effectively classical? So what is it? Two quotes. I'm not going to do an extensive amount of quoting, but I'm going to give you these two passages and then illustrate with a simple example how decoherence works. And then I want to discuss the implications for the claim that decoherence explains classicality. So what do we have? We have Zurich and Paz saying a little over 10 years ago, the line is pretty much the same today. Decoherence is the process of loss of phase coherence by the system caused by the interaction with the external or internal degrees of freedom, which cannot be followed by the observer and are summarily called the environment. Different states in the Hilbert space of the system of interest show various degrees of susceptibility to decoherence. States which are least susceptible, and these are going to be important, in other words, take longest to decohere, or don't decohere at all, form the preferred basis, also known as the pointer basis in the context of quantum measurement. Preferred states are singled out by the interaction between the system and the environment. I'll take that later. In this way, environment-induced super-selection rules arise. This is a kind of, well, this is their lingo, okay? This is an ordinary super-selection rule. It's supposed to point toward an effective kind of super-selection. In other words, it's an effective selection of a bunch of states, a small set of states which might be associated with a classical, with a macroscopic object, in virtue of which one might call it classical. That's the effective, that's why this terminology is used. So in this way, environment-induced super-selection rules arise, which effectively outlaw arbitrary superposition. So the idea is you're going to get rid of Schrödinger cats. Thus, even though the superposition principle is valid in a closed quantum system, it is invalidated by decoherence for systems interacting with their environments. Right? So this looks paradoxical, potentially. All it really is saying is that if you have a system interacting with an environment and you evolve the whole thing as a closed quantum system, but if you look at the reduced state of the subsystem of interest at the end of the interaction, it will experience decoherence. Right? So all evolution here is unitary, because one is that all the evolution has to do with the system as a whole. There is a kind of decoherence you get in black hole evaporation that people have argued about, which is a non-unitary evolution which gives rise. This is the whole black hole information loss program. only thing I'm going to say about quantum field theory. Right? Okay, so quantum field theory conference, I have to get this in. So there you have an initial pure state evolving to a mixed state, and which is obviously non-unitary, but it's a closed system, arguably. Here, the closed system evolves completely unitarily, but the subsystems display this environmentally induced super selection. We'll see it in an example if you haven't seen stuff before in a clearer update in a moment. One other claim of the same ilk: typical classical properties such as localization in space are created by the environment in an irreversible process and are therefore not inherent attributes of macroscopic objects. The features of the interaction define what is classical by selecting a certain basis in Hilbert space. So in other words, what this means is that the preferred basis in which the decoherence takes place, the preferred set of pointer states, is a function of the Hamiltonian governing the evolution of the system and the environment and their interaction. Hence, super selection sectors emerge from the dynamics. Okay, let me move on. We can talk about that a lot. There's a lot built into this, including the problematic notion of the irreversible process. But let me move on and discuss the simple example, which I associate with Zurich. I'm not sure if he originated it. It's called the central spin model. And it's a toy model for decoherence. It consists of a central qubit. I'll show you a picture in a second. So it's a qubit is just a two-state spin system interacting with n other qubits, which we are to regard as the environment via this Hamiltonian, where I sub I is the identity matrix for the I system. Okay, so in this simple model, there's no self-Hamiltonian for the individual qubits. And the interactions are only between the central qubit and the individual environmental qubits. So what does this mean? It means there's no evolution at all for the systems on their own, for each of the subsystems. The only evolution has to do with the interaction between those bits. And the interaction is of this form. Basically, the central qubit is interacting with each environmental qubit. The environmental qubits are not interacting with each other. And the decoherence, the interaction is parameterized by a coupling string. And the decoherence comes from the fact that these, for a large number of qubits, if you regard, if these are different, if the G's have different values, which they affect, they do graphically here, that's why the lines are different, then the G is effectively, it gives a period to the evolution. It's a kind of a rotation around in this case, the z-axis. And this rotation for each sub-evolution occurs with a different frequency. So effectively, you get cancellation of the summing over a whole bunch of different sine waves with different frequencies. So this is the result. If n is sufficiently large, then as long as the coupling constants, as I say, are different, if they're all the same, then you get no decoherence. Okay? As long as the coupling constants are different, so that's a fairly generic situation, you might think, the system will exhibit decoherence, and which means that an initial product state, so this is a product state of system and environment, which you might write as this is a system, environment. The environment is in some arbitrary initial state, E0. Will evolve toward an entangled state like this. And after a sufficient amount of time, T sub D, it just stands for decoherence time, has passed, these two states will be E plus and E minus, or become effectively orthogonal, and the reduced density matrix of the central spin will be well approximated like this. Okay, so in other words, the effective state of this system will look like an incoherent mixture of plus z and minus z. These are just the projection operators of the plus z and minus z states. And these are the original the squares of the original amplitudes associated with the spin system. So this looks a lot like the kind of a model of measurement given by von Neumann. Is this type 1? Type 2, I forget. Anyway, this is a kind of quasi measurement. You get, it's not a measurement, you don't get a single outcome, but you get a density matrix to which assigns a kind of a quasi-classical probability to each of these two outcomes. Each of these two possible values of this spin. So the fact that the initially pure rho sub s evolves toward a convex combination of projections on the preferred pointer states. So these plus z and minus z are the pointer states. These are the sort of the surrogates for classical states. Is an example of an environment-induced superselection or Ein selection. Right? So these are preferred in the sense that this density matrix is not going to take this form if I wrote it in the x basis. Okay, it doesn't do anything interesting. The x basis is not singled out. It takes a particularly simple form in the z basis. Graphically, this is what's going on. So I'll just take a second to explain. This is supposed to be a representation. My limited graphical skills of the block sphere, the states of the central spin. Right, so this is just a way of representing the possible states associated with a single qubit. This is the plus. This is the y-axis, x, z. So this is a plus z pure state is up here. This is a minus z pure state. These are all the boundaries of the sphere. The plus y will be up here. The plus x over here. Things in the interior are mixtures of plus z, minus z, plus x, minus x, slightly in different ways. And what decoherence is doing is it's driving states which are not on the z-axis in toward the z-axis. So you get a kind of compression. This is what suggests the imagery of Ein selection. Okay? That in a short amount of time, this qubit is going to be, wherever it started out here, is going to end up somewhere on the z-axis. Okay. So, pointer states are classical in the sense that they represent classical properties with definite values which evolve in a continuous fashion. All right, so I should say first that, spin is not a classical property. This is a toy model. Angular momentum is a classical property, but the idea is that this also happens with most notably position, but arguably in many physically plausible cases, it happens approximately in the position of momentum cases. So what you have are properties which represent paradigmatically classical observables, which appear to take let me back up. The pointer states. A pointer state here is not just any state on the z-axis. A pointer state is either, it's either this state, or this state, again here. So what these do is they given that interaction, something that starts here is going to stay here. All right, it's going to starts in a minus z state, it stays in a minus z state. And in fact, it doesn't decohere at all. It doesn't lose any purity. It maintains its purity. Same thing with a plus z state. A coherent superposition of plus z and minus z is going to lose, which could be out here, for instance, or here, is going to lose purity, is going to decohere and exist in here. So the point of this first bullet is that for the particular states that are pointer states, so these are not like Schrödinger cat states, these are like Schrödinger's cat before it gets exposed to this horrible apparatus. Schrödinger's living cat, so a living cat tends to remain alive. So it's interesting, it's a remarkable property I wrote. It shows how appropriate sorts of environmental interactions allow a system in a pure quantum state, which is an eigenstate of some classical observable, like position, to behave in a classical manner. So one of the things that this was used to explain is why, you study a free particle when you're taking introductory quantum mechanics course, then you find out, well, a free particle, it can have a fairly definite position, fairly sharp position at t equals 0, and you let it evolve freely. And what happens? I mean, the position gets totally spread out all over the place, becomes completely indefinite. That doesn't really look like much of a particle. There's nothing that looks like a trajectory associated with that thing. So this is giving you a kind of a model where by interacting with the appropriate environment, a particle can maintain an approximately definite position over time, and thus have an approximate trajectory associated. All right, so that's interesting. Now, systems which are in superpositions of pointer states will experience non-trivial evolution. This is what I just said. And they wind up in general in mixtures of pointer states. And these mixtures effectively assign probabilities to the different pointer states and thus resemble classical probability distributions. This originally led Zurich in 81 and 82 to say that he had solved the measurement problem. He was taking the task over the next 10 years or so for this claim, and eventually backed off it. And to a claim that what these represent, in other words, associating these mixtures of pointer states with particular subsystems represents the emergence of a kind of quasi-classicality. So, depending on what you read in the literature, sometimes this is not qualified with quasi, but that really is the meaning. Is quasi, at least in the sense that there is not, that there's no definite property associated with the subsystem. There's an ensemble. And it's a single subsystem. This is something that Z is often at pains to emphasize. It's reiterated several times that the mixtures are improper mixtures. Okay, which means they're not, you can't associate them with ensembles. So the thought seems to be that in some sense, these subsystems which are described by mixtures of pointer states appear classical. Now, this again is just sort of repeating the point up here. Suppose that Schrödinger's cat is interacting with an environment in such a way that live and dead are pointer states. A living cat will remain living, and a dead cat will remain dead. Okay, so that's the first point. And then a cat in a coherent superposition of live and dead will evolve into a quasi-classical mixture of live and dead. All right, so what can we make of this? We might regard this as like, okay, this is interesting. These don't seem to be typical states, these quasi-classical states. Okay, admittedly they're not classical. We haven't picked out a single outcome. We haven't solved the measurement problem. Nobody said we can do everything with decoherence. Nobody said it's going to solve the measurement problem. Actually, somebody said it, then they took it back. So, but you might ask, and as I was telling Gordon before, this is a question that was sort of urged on me when I was working on this by Owen Barone. So how atypical are these mixtures? Right? I mean, should we be surprised that there's some special dynamical process that yields mixtures of pointer states? So, to answer this, well, what do? We consider a Hilbert space. Again, I'm just looking at an arbitrary system of K k qubits. So tensor product of two-dimensional, I'm sorry, k two-dimensional spaces. So we're interested in the behavior of a particular subsystem, maybe this one. What, if anything, can one say about the properties of S, of that subsystem, given an arbitrary pure state psi belonging to this open space? So, how to answer that? Consider the uniform with respect to the standard measure over this space with respect to the harm measure on UN. I guess it should be U. Well, the standard harm measure of this space, given by this density matrix. Okay, so what you're doing is you're taking these are projectors on the basis vectors of the state, and this is just an equal weighting of each basis vector. So essentially, what you're doing is taking this large space and taking a measure such that every pure state on this space is as likely, the measure defines this, but as likely as any other. So an arbitrary, I should have written this down.
Over there, you got one.
I've got a marker. What? What's that? Sorry. You want me to draw on the screen? So, on a 3-bit state, on a 3-bit system, an arbitrary state is going to look something like A equals minus plus C plus D minus plus and so on. Okay, these are the basis vectors. These are numbers, and complex numbers. Modulus less than 1 to add up to 1, who squares that out to 1. All right, so take an arbitrary pure state of however many qubits you have. That's the picture. What do you expect to see for an individual subsystem? So what we were asking about, we'd like to ask about the properties of the reduced density matrices. Those of S, which is just the trace over the environment of the density matrix over the whole, where the whole thing is described by a pure state randomly selected from our ensemble. So it's just an urn of pure states over how many k qubits, and pick one out. What do I expect? So Popescu et al. Showed that use Levy's lemma. I mean, obviously there's going to be some dispersion. It's not going to be a single value. It's going to be an average value for that state. And for the uniform ensemble, the average value, intuitively, you can tell is just going to be a completely mixed density matrix, right? So the average value over that whole ensemble for a given subsystem is going to be a completely random density matrix, so it's going to be diagonal in every instance. What this work showed recently is that for the vast majority of states, well, it sort of falls trivially for this ensemble, but there's very little deviation from the average. So any given pure state, any given subsystem from any given extracted from any pure state of the whole system is going to be extremely close to the average. So it means that any particular reduced density matrix is virtually indistinguishable from the average. This is an expression for the bound. Okay, I won't go into this, but if you want this, it's here. It comes. There's more detail in their paper. But the upshot is that is this. Okay, as long as the dimension M of a subsystem S is much smaller than the total Hilbert space dimension N, then for almost all states rho of the total system, these are the pure states that describe the whole universe of qubits, the properties of S will be essentially indistinguishable from the ensemble average from that subsystem, which is to say, case that they're indistinguishable from a maximally mixed state, which is in turn to say they behave randomly with respect to any choice of the observer.
Question for
yeah.
clarification.
Yeah, yeah.
What do you mean by almost all? You don't mean what the mathematician means by almost all. All except for major zero in some sense.
Oh. No, I don't think I need all, but
You need
zero.
vast majority in harmonic.
What's that?
You need vast majority in harmonic.
Yeah, but I don't know if there's, it's probably good, I'm sure it's measure zero when you let n go to infinity, but then there are problems.
Right.
Yes, but then there's problems with the, I don't want to let n go to infinity right now. There's other problems with that for issues. You don't have to use this measure, you don't have to use a uniform measure, you can use any other one, so I'll say something about that in a second. So the distribution on the block sphere has this form, which I'll show you a graph of. Maximally mixed states are multiples of the identity, hence effectively diagonal in any and all bases. So that's where this is going, right? So the basic point is that in an arbitrary universe, subsystems are entangled with many, many, many other subsystems in the universe, which is most of them, and they don't have any interesting identity of their own. In fact, it's an interesting question as to why our universe is any different from that, right? Because maybe in some sense it isn't. Why individual subsystems seem to have non-trivial properties. But this really grows out of an insight. It's something, ironically, that Zurich has urged for a long time. It grows out of the fact that Hilbert space is really, really big. This is how he puts it. And that the vast majority of states are massively entangled states. And so the vast majority of subsystems are described by things that are that look indistinguishable from maximally mixed states. So the point here is that, well, I'll explain, this is just an illustration of what I'm talking about. The point is that the form of density matrix that you get via decoherence turns out to be something which is quite generic, independent of any decoherence processes. Okay? And independent of the size of the system. Right, so if you just take a whole bunch of qubits, a whole box of gas, it's massively entangled, and you look at the properties of a single subsystem, you're going to get a density matrix that is more or less random, and hence diagonal in many bases of interest. The universe has, so this is just a plot of that function that I had on the previous slide. I'm going to move these quickly. This function, right? This is approximately right for k equals 2, for k equals 4 qubits. I believe that was k was the dimension of the environment, how many environmental qubits out there are. And this is a plot of where you're likely to find, this is sort of the density of a state. So this is where you're likely to find a given state. How far away from that z-axis, or actually, this is how far away from the origin of the clock sphere, which is the maximum mixed state, you're likely to find a mixed state. And you can see that even for very modest environments, this thing is super ridiculously sharply peaked at the center. So almost all the states are looking at that. And this is a kind of a funny result, only in that you can I've talked to many physicists about this. Some physicists are astonished, some physicists think that this is just totally obvious. It depends. People in quantum information tend to know this. Okay, people outside of quantum information don't think like this. Okay, so quasi-classicality again. So this is, let me get back. That's as much technical stuff as I want to do. Let me draw some morals from this. almost all states of all subsystems are and remain quasi-classical in the sense that research by Zurich is selected from the uniform ensemble. And if you generalize, so you don't want to use the uniform ensemble, you might say, well, why are we picking just arbitrary states? Okay, if I generalize, if I take n goes to infinity, if I take, and I want to generalize your model, my uniform ensemble is an infinite temperature ensemble, right? Because the energy is unbounded from above. You have an infinite number of bits, and they can all be have a positive energy. The energy is going to add up to as high as you like. So what's the temperature associated with that ensemble? It doesn't look anything like our world. All right, so you might say, okay, I want to use a more reasonable ensemble. Now, what's reasonable and what isn't reasonable is, of course, related to the exit problem of defining typicality. Okay, this is an old problem in thermodynamics. What do we think? What is our sort of reference class of states? Use a microcanonical ensemble, the states which are a small distance away from a particular fixed energy. Using that ensemble, a given subsystem may or may not be diagonal on the basis of interest. It will be in energy. But either way, it will be unaffected by decoherence because any such ensemble, if the ensemble is stationary, nothing is going to happen.
So Stephen, I missed the step. Where did we get the station from?
I stipulated it for an arbitrary, so that's a NC, yeah. You don't have to use a stationary ensemble, but then it becomes a question of if you use a non-stationary ensemble, what is it that makes it represent sort of a generic set of states? So quasi-classicality is heretofore defined, appears to be an entirely generic property of certain ensembles, and moreover, is in any case independent of any selection-inducing dynamics. Okay? So decoherence isn't really doing any work on this whole ensemble of states. Dynamical decoherence only operates on special systems like Schrödinger cats, things that live, for instance, on the boundary of that block sphere. The state of the cat after decoherence is, however, not significantly different from that of a generic microscopic system. Thus, Schrödinger cats don't evolve to a state of any special interest in general. Suggests to me that if you want to pursue this approach, you need to adopt a more restrictive and interesting notion of quasi-classicality. In particular, I would just say that it's not clear how the one we've adopted, which just focuses on the properties of the diagonalization of the density matrix of the subsystem, how this saves the appearances. In fact, there's nothing in there about the appearances. How do these things look to observers? Well, we haven't represented observers in the theory as I've presented it. So who's to say how these things look? All right. So this motivates this further development of the decoherence program. So let me just read this quickly. It's an attempt to add a further condition for quasi-classicality, so to sort of embellish the characterization, a stronger sense of quasi-classical. Recently, the environment has started to become interesting again, because I have decided it will. The most obvious feature that distinguishes the classical realm from the quantum is objectivity. The first thing that popped in everyone's head. Unknown classical states can be found out without being disturbed, so they are said to, quote, exist objectively. This is, of course, so what you're getting here is it's a kind of, it's objectivity as a kind of intersubjectivity. This is, of course, not the case for quantum states. It's often been emphasized by Paris that the nature of a quantum state is a much more elusive thing. In quantum systems, at least isolated ones, such states cannot be regarded as existing objectively. As was pointed out some time ago, however, observers usually obtain information about a system by measuring its environment. Okay? You don't interact with the system directly. You shine some light on it, and what you pick up is the reflected light. That's the intuition here. Fair enough. Therefore, the manner in which the environment stores and transmits information is of great interest. In a sense, the environment is not just a wastebasket where quantum information gets thrown away, which essential as is in those original decoherence models. You never look at the environment, but rather a communication channel through which observers find out about their universe. In this quote, environment is a witness view of the transition from quantum to classical. Objectivity is a consequence of the redundancy with which information is inscribed in E. So classicality or quasi-classicality is going to have to do with redundant storage of information in the environment. Okay, so just a caveat here, the observer is still here, not been integrated into the system, so it's not entirely clear what an observer is going to observe, hence how the appearances are to be saved, and hence how you get any real intersubjectivity. But it seems like it's a potentially interesting criterion. But at least this additional criterion has the potential to discriminate between macroscopic and microscopic. So in the basic decoherence time selection paradigm, the environment is only a witness in a really minimal sense. One would have to measure the state of the entire environment in order to ascertain the state of the subsystem in question. That's what those original models look like. Here, well, never mind about there's a little qualification there about knowing the initial state. But what they're looking for is redundant encoding of information in the environment. Okay? And what you need is, the point here is that you need an appropriate environment. Okay? It's not going to work for an arbitrary environment. You can tell that the environment is a communication channel, but if the communication channel is arbitrarily noisy, it's not going to redundantly encode the information. Yeah?
So is this any different from the old argument about how a quantum particle can make a classical-looking cloud chamber trap?
That's the argument of Mott, right? Is that the one I'm referring to?
I think so.
I think that was a sort of an environment as measuring apparatus thing. I think it's related to that. In that what you want is you want this quantum system to sort of leave its mark successively on several parts of the environment, which are the pieces of the cloud chamber, leave us with several subsystems. But and the point here, so it's a good example, is that you have to prepare a cloud chamber. It's a special sort of, it's not an arbitrary quantum system. Now, let me read this because it brings out a very sort of interesting turn of phrase here at the end. The results of the previous section of the paper here indicate that the vast majority of states are arbitrary multi-spin environments. This is a paper in which they're looking at this sort of redundant encoding of information in the context of one of those central spin models, are non-redundant encoding states in which information is recorded so that multiple observers can never independently measure the same system. Our everyday experience, however, contradicts this result. All right? By intercepting a tiny fraction of the photons or phonons which scatter off or are emitted by another human being, we obtain a great deal of information about their appearance or speech. Moreover, hundreds or thousands of other human beings obtain essentially the same information, especially if you're on Facebook. We are thus led to conjecture that the ensemble of system environment states produced by natural processes is substantially different from the ensemble of all states. All right, so this, what you have here is a concession that this redundant encoding doesn't work for an arbitrary environment. What you have here is a kind of puzzling suggestion that the dynamics that govern our world are such that systems and environments, that there are special system environment states which are such that the environment does redundantly encode things. All right, so that somehow generic dynamics, these are generic unitary operators, somehow there's a suggestion here of something which is really impossible. Okay, that you take arbitrary states and you drive them into a smaller region of Hilbert space, which is one in which you can encode subsystems can redundantly encode information about themselves in the environment. Okay, so I think what you're you're seeing here is a real tension in the program. An attempt, it's a reflection of the fact that the decoherence program is intended to show classicality as a generic emergent feature for suitably macroscopic systems, but is unable to really achieve that. Okay, that you either need a very weak notion of quasi-classicality, whereby decoherence plays no role, whereby almost all systems are quasi-classical, or a stronger notion, in which case the state of the world, in particular the state of the environment, is going to play an important role and so what you're going to find is that arbitrary systems in arbitrary worlds are not going to appear quasi-classical. Okay, so the conclusions, I see them 1 minute over. 5 pages of conclusions, that's a very significant paper. Decoherence doesn't explain the emergence of classicality simpliciter. This is what I just said. Let me not go over that. I do think this is interesting. I do think that the phenomenon known as ion selection, which is one of the first things that Surik identified about 25 years ago, explains the persistence of classicality in that it explains how a particle can exhibit a roughly well-defined trajectory despite, or rather because of, continued non-decoherent interaction with the environment. And so it explains how macroscopic objects can retain more or less definite properties despite the fact that they're described in quantum states. If we start with a classical world and we're given appropriate interactions, we can maintain a classical world. What remains to be explained is what happens when an interaction somehow, despite the ubiquity of environmentally induced decoherence and ion selection, manages to give rise to a superposition of pointer states. Okay, so this is just a question of what, how do we interpret these density matrices, which is the superposition of pointer states. It's like, so the idea is the creation, what happens when you create a Schrödinger cat? What happens next? It does interact with the environment. What implications does that have for classicality? I think it's not clear. But even more important, I think, is how do such deviant interactions arise in the first place? So if you assume that decoherence and ion selection generating Hamiltonians are typical Hamiltonians in a world governed by the physics of the standard model, and this is the kind of rhetoric you find a lot. So all the Hamiltonians, obviously, are, like the one I wrote down for the central spin model, are effective Hamiltonians. They're not written down in terms of fundamental quantum fields. But it's felt by many who work in this that the properties of those, in particular properties, their tendency to localize things in position and momentum space, has something to do with properties of the fundamental interactions underlying them. Okay, so these should be generic. But then the generation of macroscopic superpositions, given such Hamiltonians, would seem to be a sort of a miracle on the order of a Poincare recurrence, which is really to say, how the hell do you manage to prepare a pure state? Okay, everything is interacting with everything else. Classical things, given that they exist, maintain their classicality in virtue of these interactions. That's the assumption. These are the typical Hamiltonians, which have classical pointer states. But then we can produce, perhaps short-lived, but we can produce macroscopic superpositions. How? How do you ever generate a pure state, well, of anything, much less a macroscopic object, from a universe which is massively entangled? I think that's an interesting question. Last implications, I will just say here, I found one of the ways I got started on this was thinking about many worlds interpretations and the implication of decoherence as a plausible physical mechanism for solving the basis problem, the preferred basis problem, and the generation of branches. So I think it's interesting to explore the implications of this for senses of classicality which are meant to apply to many worlds interpretations. I think there's an additional question here, but I think I'm not going to, this is maybe too much to elaborate this information loss and the connection with the arrow of decoherence with the thermodynamic arrow. So I think it's interesting to explore, but it's too much to elaborate right now, so I will stop. Take questions.
Okay, well, I can probably go on to a shut up, so I'll ask a couple of things. I mean, if you make a technical sort of comment first, I mean, the question of how we come to find superpositions given this kind of thing, and inversely the idea that what we're getting out of decoherence is generically stable trajectories, which we wouldn't have random. I mean, those things are quite sensitive to the kind of dynamics I've got going on. So on the one hand, if I've got the sort of details of the dynamics going on, not back in the way you need, that you can say. I mean, say I've got a classical dynamics that's regular but non-chaotic, then yeah, sure, decoherence is going to mean that states are not going to spread out. But of course, if those things are macroscopic, we already know that in a very regular dynamics, then wave packets with big masses don't spread much anyway. Now, conversely, if my dynamics are chaotic, we've got a lot of large electrons which have reason to think that take a chaotic system, apply decoherence, and you will absolutely have the development of superpositions. What you won't have is the possibility of infinity experiments. But say there is a paper of Jürgen Paz where they say you take one of the moons of Saturn, I think it is, which is classically chaotic. How long will it take to make quantum superposition? A few years. And if you do this for small scale things like weather, it's going to happen in a few days. It's generically going to happen on a few multiples of the chaotic, of the general time scale of the chaotic process. So I think there's a kind of relatively direct dynamic answer to that question. It's about that kind of allowing a dynamical process, classically speaking, you're extremely sensitive to initial conditions. And you might well know, except for what those are doing there.
That's more what I have in mind. Like, what are those? I mean, there's a sort of a pretense, arguably in this work, to take the Hamiltonians that are studied as kind of generic.
Right, but I'm saying some of the Hamiltonians in the study are non-chaotic, it's non-chaotic. It's not a chaotic one, and it does not have the property of ensuring trajectories. It gives you a stochastic.
Right, okay.
I mean, the other thing, now that we're technical, the non-technical kind of question straight comment, I mean, yeah, absolutely, generic systems are going to not provide interesting architecture. Yeah, absolutely, in many worlds framework, it's committed to a very limited set of universal quantum states. It's not clear to me that should be at all problematic. I mean, we know, we knew from classical statistical mechanics, class quantum mechanics, that generic states are incredibly boring. Generic states are just basically very hot and sit there going on. I mean, we've got strong reason inside the Subsystems that believing in the universe really is rather highly anomalous in that sense. And perhaps that links to the comment you can have quickly made in the last bullet point there, the link for thermodynamics over time.
Well, that comment is really sort of directed toward the remark that decoherence and dissipation are different things, right? So it's sort of, so certainly occur at different time scales, and you might conjecture that you have decoherence in one direction, and dissipation of energy in the other direction. The question is just how much do these come apart? Which is related to the question, the other question you're asking. So if we're on with some special conditions for the universe, special with respect to what? To thermal entropy, or employment entropy, or all across the board?
I guess my feeling is that straightforward observation very directly falsifies the idea that the state of the universe is remotely typical in a very large number of possible ways. That typical means typical with respect to any of the dynamically natural neighbours of any of the spaces you have known. The universe is clearly dramatically and wildly atypical. So I don't find myself very worried by what would happen in different cases.
Yeah, I think this depends on what you take the notion of what's the goal of the explanatory project. In other words, in one sense, it's obvious the universe is atypical, right? Because the universe is presumably one state, and that state is going to be measure zero with respect to any normal distribution. So, but we still think we have things to explain that some phenomena are more or less. So the question, go ahead.
I guess it seems almost to be a kind of argument against using the kind of measures in play. I mean, on more or less any interpretation of quantum mechanics that I think of, state physical space at random for the universe using the Hall measure, and that state is going to be wildly also observation. In case it's never easy to get, but in any other theory, it's going to correspond to an incredibly hot, very uniform plasma.
True.
Okay. Oh, go ahead.
Well, I mean, the one thing is that I'm not clear on, maybe we could discuss it once. It's not clear exactly what notion of quasi-classicality you would use coming from this program in a many-modes interpretation. I understand how it's done in decoherent histories, okay, what the branching structure is, possibly the first grain or sets of observables. And the quasi-classicality is a property of entire histories. Here, it's something which can emerge dynamically. And the worry I had, one worry, is if you take the weak notion of quasi-classicality, you can have any branching structure we want for an arbitrary one. And then that looks empty. I mean, it looks like quasi-classicality of cheap. So then you want to strengthen it, and then the question is how do you strengthen it? This is one way. This environment is a witness thing. You're building in a sense of intersubjectivity. It's a way of strengthening it, but I think that ultimately what's lacking still is characterization of the observer. So you really ultimately want to say the appearances, but you need something that will correspond to the appearances.
So I think I draw less of a gap between this and decoherent. And you got to get rid of a lot of time to analyze stories. I'll gush that out now.
We come back.
Yeah. I don't think that we would have ever been convinced, assuming this is a quantum world, I don't think we would have ever become convinced that at the macroscopic level it was a classical world, just because an environment with a high number of degrees of freedom tended to drive the states of subsystems into improbably mixed states with certain characteristics. There's an additional feature that seemed to be missing to me in this presentation, and that was it's got to be difficult to the point of effective impossibility to measure what I'm going to call entanglement observables. Observables that are not properties of the systems in question, but are properties of the coupling of the systems to the degrees of freedom of the environment. There are some such observables that we can measure. You made reference to reflected light and stuff like that.
Right.
But there's such a wealth of such observables that we have no effective access to observation. And it's because of that absence that over history we have evolved into the illusion that we live in a classical world at a macroscopic level. And it doesn't just come from the high number of degrees of freedom in the environment, because most of these toy models that people talk about, they can have very high numbers of degrees of freedom, but they're pretty simple so that you can do the calculations easily. And it's not too difficult to describe these entanglement observables that I'm talking about, and thinking about the possibility of measuring them so that you could elicit, could extract the quantum feature of the system of interest, even though it wasn't manifested in what we would call the properties of the system of interest. So I think it's very important that the interactions between the environmental degrees of freedom and the degrees of freedom comprising the system of interest are of such a subtle nature as to deprive us of observational access to the vast wealth of entangled observables. That's an additional requirement.
Classicality. But that seems to run against the environmental witness program.
To some extent it does, yes. In other words, if
Running away from it doesn't
the kind of inaccessibility of these entanglement observables were not there, the environment could be a much more informative witness about the systems, informing us of the system's quantum mechanical properties, and not just of the properties that we think of as classical.
Right, but then what do you say? So what would you say then about that? Somebody said, well, then you're calling classical and arbitrary. Well, this is the tricky thing. So I was going to say what you're calling classical, an arbitrary microscopic system that's going to interact with other microscopic systems.
Well, microscopic systems aren't classical. we have access to the entanglement observables of microscopic systems, and so we see their quantum mechanical behavior.
Well, but you, if you prepare them to do, right? I mean, what's the,
We detect muons that came from cosmic rays.
Electron shells and atoms.
Yeah, we subject them to magnetic fields. We catch them as we can. I mean, we like to prepare them. We can, but we don't have to.
no, I'm thinking more of a box of gas. You're taking one flip, you want to ask about the state of an arbitrary subsystem. It looks like a massive mixed state. It's clearly entangled with all the other molecules in the box of gas. Now, the thing is, if you don't know what the initial state of this system was, this entanglement information is not going to tell you. So if you measure the whole environment, you're going to know that the environment is entangled with this one little particle.
I agree that there are microscopic systems in situations, in circumstances, where even for them,
Yeah.
access to the entanglement observables is for all practical purposes denied to us.
Right.
My claim is that the nature of the interactions between high number of degrees of freedom environment and macroscopic physical systems is such that we essentially never have access to the entanglement observables, and therefore we can never see the quantum mechanical properties of those macroscopic systems. Now we keep, nanotechnology keeps advancing by leaps and bounds, and who knows, but one day we may see Schrodinger's virus, or Schrodinger's biological cell, or so on, enough to scale, and who knows how far it will go. But my claim is there's a feature about the nature of the interactions between the degrees of freedom of concern here that is very essential to denying us easy access to the quantum mechanical features of macroscopic systems. It's not just that there's a large number of degrees of freedoms, and I suspect it's not just, for instance, in the model you mentioned, you said the G, the coupling constant, the G's had to be different. If they were the same, it would work. Yeah, they do have to be different, but in a model that simple, I doubt that even that would really deny us access to the entanglement observables. But I'm guessing there, that that's the case.
Okay.
Yeah, so I think Max Schlosshauer has just written a really nice paper that talks about that point and as exactly why we don't observe, say, superpositions of Hyperion or something. But my question for you, Steve, is just, so one of your takeaway points is the claim that emergence can't come out of decoherence, or at least it doesn't in such a widespread way that maybe we want it to. Can you be more precise about what you mean by emergence? I mean, is it related to how you define quasi-classicality then, or?
Yeah, well, it certainly is. So, I mean, to recap, there's
Sorry, maybe that was the first part that I missed.
Oh, right, okay, yes. So, yes, there were two senses of quasi-classical. And in one sense, the idea was that quasi-classicality is a generic feature if you define it in a sort of weak sense, in the sense that you just have subsystem density matrices in effectively diagonalized classical observables. So then everything looks, too many things look, this is part of what we just discussed here, I guess, quasi-classical. If you define quasi-classical, if you have the additional requirement, as these guys want to do, that quasi-classical means that the system has some objective properties which correspond to having its property redundantly encoded in the environment, then it looks much more special, thus not explained.
Sorry,
Or what would explain quasi-classicality lies as much in the state, in the initial state of the environment, as it does in any particular unselected dynamics. So, right, in one sense, a quasi-classical, it looks like a generic property of all quantum systems, macro and micro. In the other sense, it looks like a very special property, and thus arguably not explained. But as I think is emerging here, I think this is the tricky thing about it. One of the tricky things about this subject, what exactly is the explanatory task? What is it that we think we don't understand or want to understand? And I'm not sure that's consistent across people who apply these techniques. So people who do this in quantum cosmology can see a little of this, talking about the decoherence of the inflationary perturbations and the emergence of structure. They're really looking at very specific models of the early universe with very special states, and they're trying to explain the emergence of structure just within those models. So that's not taking an arbitrary state of the universe and asking for classical behavior. That's picking a particular state and looking for very special behavior. Very what we're looking for is is the emergence of density, Gaussian density perturbations.
Steve, just wanted to ask. Steve, just wanted to ask whether in literature there's, or whether you have up your sleeve, or whether in the literature these people give a more precise definition of what environment is, because even going back to the toy model of the kind of the central qubit,
right.
yeah, central spin model. I mean, so just kind of by fiat we say, all right, the environment qubits don't interact with each other, but that's not a generic situation, because in a generic situation, of course, the environment bits would interact with each other. So, I mean, is this just a kind of stipulative, case-by-case division between environment and subsystem, or is there a more blinding understanding of, oh, okay, environment just going to be some kind of non-dynamical background where the subsystem just doesn't exert, well, either A, the subsystem doesn't exert an influence on the environment, or B, the environment is not somehow self-interacting.
Right. I mean, it's a little of both, and it depends on the context. So, in some sense, what that model of the interaction is sort of is there instead of giving any other macroscopic characteristics to the central spin. Because the central spin is just another spin. So, what's special about it? Not that it's heavier than the other spins, but that really what's important is its interactions with the other spins totally dominates any interactions that the other spins have with themselves. So there it's kind of asserting. But people have done, people who are interested in, I think, control and decoherence in quantum computers are sometimes think about it differently, in that they really think of these things as things that you might be able to control. So the idea, one idea I've seen floated, I don't know if it works, is you can have one system interacting with an environment, which might tend to decohere it, but if the environment has enough of a strong enough self-interaction, that actually precludes it becoming entangled with the subsystem that's supposed to perform whatever computation you're asking. But yeah, you're right. I mean, to some extent, this is it's not a problem that it's arbitrary what you call the system and what you call the environment, but we start attributing different dynamical properties to systems and environments. You get really caught up in the self-Hamiltonian of the environment, the self-Hamiltonian of the system. And I think these questions are good questions.
So,
Yeah.
I'm always really struck by the fact that people talk about decoherence and never mention the DLP program, Danieri on Europe is very the old basically decoherence program in which you're supposed to model the environment, the interaction between the system and the environment, and pray there's ergodicity or some sort of stronger dynamical instability property, and that's supposed to wipe out the entanglements. Now, it doesn't solve the measurement problem, but then again, neither does this. But
Right.
So I guess my question is, there seem to be two things going on in the whole decoherence program, and I'm definitely not an expert on this, but on the one hand, you've got the idea that the environment is this vast number of particles or whatever, and somehow that's supposed to give us an account, just the vastness of the interaction between the single system and the rest of it. But also somehow there's supposed to be some sort of dynamical interaction, and it seems in some instances the one gets emphasized, and in other instances the other gets emphasized. So David Wallace mentioned the chaotic nature, then we've got a dynamical account maybe of what's going on. And it seems to me to be this parallel between sort of different ways people try to justify the use of, say, the microcanonical method to explain, gives phase averaging, you've got the Kinshin kind of approach, which just appeals to large numbers of degrees of freedom and kind of ignores dynamics and looks for peak Gaussians, right? Versus an ergodic kind of approach. So are there, how do these two things fit together in the decoherence?
Yeah.
Sort of do that?
Well, that's interesting because I mean, I'm just, the approach I took, just looking at generic states sort of corresponds to the non-dynamical
Right.
approach. What does a typical state look like? And then, yes, obviously, the Zurich programs do lean heavily on the dynamics. It's because we have certain kinds of interactions.
Right, but they never tell us what those interactions really are like. I mean, presumably we can get, if you look at the Hyperion example, you actually know what the
Right, although that example apparently is a little bit, I think Schlosshauer's paper was a sort of critique of Zurich.
So any chaos.
What the moral of this was, yeah, this was the, yeah. Right, the problem is, I mean, it's a much more general problem with thermodynamics. I mean, thermodynamics, at least the equilibrium thermodynamics, is a much simpler set of interactions that you're dealing with, and it's already problematic. What you're effectively looking at here are systems that are out of equilibrium. And in fact, some of the follow-up paper of Fescue, Short, and Winter looks at sort of the dynamical approach to this ensemble, like how systems which are not nearby this typical state, this average state, how do they evolve? I'm not sure I'm answering your question, but it's just
more of a comment.
yeah, the feature, I mean, it's kind of piecemeal. I'd say that the dynamics proposed are supposed to look like typical sort of lab dynamics, or in the case of cosmology, they're supposed to derive from the effective field theories that are driving the evolution of the early universe. So that's the worry here, I would say, and this was raised to me by a friend who works in also in quantum information, is that, you know, effective dynamics are a product both of the underlying, you know, dynamics given by the standard law, in other words, the fundamental physical laws, and the states. Right, so that what you're doing when you're assuming an effective Hamiltonian is you're building in some assumption about how the matter is configured. And so it's not really clear what a generic Hamiltonian looks like. I mean, you can work with this, you know, just a standard model, but then good luck to you. You're not going to build a simple spin model out of the QED with logic. Yeah,
I mean, a quick observation.
good, yeah.
Almost a tough observation. I mean, I guess thinking about the question of where pure states come back in this framework, I guess the overarching answer would be that aren't they? What happens is that we can make states pure relative to us, but in doing so we pay the price that we ourselves become highly impure. If one state becomes a highly impure, so we branch. But that's this. A concern, I think, that answer your comment about cosmology. I mean, yeah, absolutely, those guys are not doing it in the case. It's not saying, look, here's why generic states ought to be this. I'm not sure anyone else. I mean, no one in I said, for instance. I wonder if that's actually not a position to be in the first place.
You mean you're wondering if this is sort of strong?
Not the issue generally. I think that would be a particular bit of it. But yes, I suppose yes, insofar as the concern is people who are trying to do this for a generic starting point.
Right, and you know, there is, I think that there is a real thread of that through the work of Zurich, and that's what explains, I think that's where this comment is coming from, okay? That he's, and you could argue that maybe you should, that, you know, it's just trying to do too much, okay? You can't squeeze classicality out of arbitrary states, any meaningful sense of classicality you're going to require. And if you don't want to, that's not the explanatory project you should be interested in. But But it is interesting that, I mean, I've said this, I gave a talk and said, about a year ago, and I made this general claim that arbitrary worlds, worlds described by arbitrary quantum states are not classical or quasi-classical, and there were some really, good physicists who were surprised with it. So I don't think that people necessarily think, I think, as is the case with lots of times with physicists, they reason with two inconsistent views in their head. I mean, you can really see this, it doesn't have to do with this, but, well, let me not go into some tangent. I've seen it a lot, and so I think it's at least worth straightening out, but I take your point that you might not think that this is a project that one should be interested in. I'm still not quite clear how the many worlds program really, and how the appearances are really safe. How the observer is built in, but that's a little much to tackle in our discussion.
Okay, let's, one more question.
So, I mean, if we forget for a second about, arbitrary states and arbitrary Hamiltonians and just think about the early universe case, is there a convincing story for how quantum states of fluctuating scalar field become classical density perturbations? And if so, what is that story, and how does it sort of differ from, these other cases where it doesn't work?
I really have a lot of time. There's a whole slew of papers on this. I mean, the story is, it's not simple. It has to do with, I think, I can't. There is a kind of an interaction that's supposed to be between short and long wavelength modes of the field. It's supposed to generate decoherence. What you get is you get a kind of quasi-classicality. There's certainly no claim that the measurement problem is solved, but the claim is that you get sort of effective classical distributions which described by these density matrices which mirror what you observe in the regular effect. So there are papers by Cliff Burgess, has a nice one from McMaster a couple years ago. There's a small literature on this from the last, I'd say, 15, 20 years.
But do you find her story convincing?
Don't know, really. I mean, I haven't really, I was more concerned with the claim that decoherence was a generic explanation for classicality rather than whether it could explain classicality in a particular context of inflationary cosmology. So, I'm going to non-committal on that. Good question.
Dennis, thanks.